Welcome to lecture 2. So in this lecture we'll talk about power functions and polynomial functions. So after you complete this lecture, you should be able to identify power functions, identify the end behavior of power functions, identify polynomial functions, and also identify the degree and the leading coefficient of polynomial functions. So let's start with power functions. What is a power function? A power function is something that can be represented by the formula f of x equal to kx power p, where p, k and p are real numbers and k here is called as the coefficient. So these are some examples: f of x equal to 1, f of x equal to x, f of x equal to x square, x cube, 1 by x square, root x and cubed root x. So here they have given us a problem to identify which functions are power functions. Let's take the first example here. So if you further simplify the first example, it becomes 8x power 4. Notice that it is in the form kx to the power p, so which means this here is an example of a power function. So this second one here, notice the second one here has two separate parts, which means that this is not a power function, and this is dividing each other, and there is no common way of writing it in the form of kx power p, so this is also not a power function. So next let's talk about the end behavior of power functions. So there are two main behaviors based on the power of the function. So we classify them based on their power, the n value, the power. So if you take an x where f of x equal to kx power n, so where n is a non-negative integer, so we can identify the end behavior based on the n value. First, we have to determine whether the power is even or odd. And second is we have to determine whether the constant is positive or negative. And finally use the figure to identify the end behavior. Now, if it's an even powers, both ends are always faced upwards. In odd powers, the right end is faced upward and the left end is faced downward. Now, the higher the power, the more closer it is to the axis. So the higher the power, so the more it starts going towards the axis. So this is the behavior of power functions. Now, what happens when you have a negative constant? So for a negative constant here, so notice that for a positive constant, both face upward when it's even. One faces on the right side it faces upward, on the left side it faces downward when it is odd. For a negative constant, both ends will face, when it's a negative constant and the power is even, both ends will face downward. When it is negative constant and the power is odd, the left one will face downward, the right one will face upward. So for an even power, the domain, so for an even power, the domain is from negative infinity to infinity. But the range generally is from 0 to infinity. But here, for odd powers, both the domain and range are from negative infinity to infinity. The range is also from negative infinity to infinity. For negative power with an even power here, so the domain will stay the same, which is negative infinity to infinity. But the range here will become negative infinity, 0. So negative infinity, 0. So this is the range and domain of the values. So here they have given us some problems. So use the principles that we just talked about and try to determine the end behavior of the graphs. So pause the video right here and try to solve this problem. Next, let's talk about polynomial functions. What is a polynomial function? A polynomial function can be written in the form a(n)xn plus a2x2 plus and so on a1x. So a simple form of a polynomial function f of x is a(n)x power n plus a(n minus 1 x power n minus 1 plus and so on plus a3x cube plus a2x square plus a1x plus a0. So this is an example of a general polynomial function. Here the value a here represents the coefficient, and it can never be 0, and each expression aixi is what we call a polynomial term, or the term of a polynomial function. Next, let's talk about the terminology here. So the a value here is called as the leading coefficient, and n here represents the degree, and the total term is called as the leading term. So because this is the one with the highest power. Now, so given a polynomial function, how do you identify the degree and the leading coefficient? First, find the highest power of x to determine the degree of the function. So the highest power itself becomes the degree. Next, identify the term that contains the highest power. So that term becomes the leading term, and the coefficient attached to the leading term becomes the leading coefficient. So let's start for this one. So what is the highest power here? So power 3. So for this one, the degree is 3. Now the leading term is the entire term, minus 5x cubed. The leading coefficient is minus 5. So use this principle now and try to solve the other two problems. So pause the video right here and try to solve the other two problems. So use the same principle again, pause the video right here and try to identify the degree, leading term and the leading coefficient of this polynomial. Next, let's talk about the end behavior of the end behavior and the degree of the polynomial. So what is the end behavior of these two polynomials here? Notice that both ends are faced upward. We know that this is a function that basically is an even function with the coefficient positive. Here also, notice that both are faced upward here. So this is a polynomial where the leading term has an even power, even degree, and the leading coefficient is positive. So the same thing here, but we apply it in a different manner. Now notice that we are not looking at the number of bends in the curve, we are only talking about the ends of the curve. So use the same principle now, pause the video right here and try to describe the end behavior and the possible degree of the polynomial function. So how would you write down the possible degree here? So notice that for 1, the x value is 3. Next, you have for -1 and 0 and 3, 0. So this is the vertex here. And how do you judge the curve here is based on the values. So determine the possible degree for this function. Now, let's take a look at how to identify the end behavior and the degree of the polynomial. So let's say they have given us a function f of x equal to minus 2x square times x minus 2 times x plus 3. So they are asking us to express the function in terms of a polynomial in general form, and then determine the leading term, degree, and the end behavior of the function. So how do you first do it? Multiply the values and try to get the final equation. So you have minus 2x square times x minus 2 times x plus 3. So when you multiply, first multiply these two. So you have minus 2x square times x square. So for FOIL method, first terms, outer terms is x and 3. Next inner terms, minus 2x. Next the last terms, minus 6. You have minus 2x square times x square plus x minus 6. Now multiply minus 2x square to each individual value. So you get minus 2x power 4, minus 2x cube, minus 12 x square. So this is f of x. So from this now, what is the degree here? So the highest power here is the degree. So this becomes the leading term. And minus 2 here is the leading coefficient. Now how to determine the end behavior? Notice that the leading term is negative, so which means that the ends will be facing downwards. And notice the degree of the power is 4, so both of them will face downwards, both ends will face downwards. So if you take a graph, so both ends will always be facing downwards. So this is how we can determine the end behavior. So use the same principle for this function here. So pause the video right here and try to solve this problem. Next, how to identify the local behavior of a polynomial function. Local behavior is inside in the curve where you go from one end to the other end. Now, so the common ones that you'll see are intercepts and turning points of a polynomial function. What is a turning point? So a turning point in a graph is the point at which the graph changes its direction, either from increasing to decreasing or from decreasing to increasing. Next, the next one is the y-intercept. Y-intercept is basically the point at which the function has an input value of 0. Basically, the point at which the curve touches the y-axis, and the x-intercept is the point where the curve touches the x-axis. So these points are called as the x-axis, and this point is the y-axis. And each end, so these 2 points here represent the turning points where the function goes from either increasing to decreasing or decreasing to increasing. Now, how to identify this based on the function that is given here? So they have given us a function f of x equal to 2 times x minus 1 times x plus 2 times x minus 3. So first things first is they've asked us to find the y and x intercept. So remember that to find the y intercept, so put y equal to 0, which is basically f of x equal to 0. And to find the x-intercept, to find the y-intercept here, put x equal to 0. To find the x-intercept, put y equal to 0. So let's take the function here, f of x equal to 2 times x minus 1 times x plus 2 times x minus 3. First things first, we have to find the y-intercept. So let's find the y-intercept. How will you find the y-intercept? Put everything in x equal to 0. So f of x becomes 2 times 0 minus 1 times 0 plus 2 times 0 minus 3. So which becomes 2 times minus 1 times 2 times minus 3. So which becomes 12. So here the y-intercept value is 12. And how will you find the x-intercept now? So put f of x equal to 0. So y equal to 0 or f of x equal to 0. So when you put f of x equal to 0, it becomes 0 equal to 2 times x minus 1 times x plus 2 times x minus 3. So from the remainder theorem, we know that we can equate each of them to the value 0. So x minus 1 equals 0, x plus 2 equals 0, and x minus 3 equals 0. So x becomes equal to 1, x equal to minus 2, and x equal to 3. So this is how we can find the, so these 3 here represent the x-intercept. So use the same principle now and try to simplify this equation first and then determine the y and the x-intercept. So pause the video right here and try to solve this problem. Next, how to identify comparing the smooth and continuous graphs. So if you have a polynomial of degree n, will have at most n x-intercepts and n minus 1 turning points. So what does it mean? For example, let's take this polynomial here. So they're asking us to determine the local behavior of the function by finding the maximum number of x-intercepts and the turning points. So a power is, so if you have a power function, the degree here is the main one that we're looking at. So degree n is the highest power 10. So the maximum x-intercepts is equal to n, so which is 10, and the maximum number of turning points will be n minus 1, which is 10 minus 1, which is 9. So remember that this is the maximum number. It can have less, but it will never have more than the actual value. So use the same principle now and try to find for this equation the number of x-intercepts and the turning points. So pause the video right here and try to solve this problem. Next, let's talk about drawing conclusions about a polynomial function from the graph. So what can we conclude about the polynomial represented by the graph shown below on its intercepts and turning points? The first thing that we need to know is the intercept and its turning point. So the intercept here, and notice that there is only one intercept. So there is one x-intercept, there is one y-intercept, and how many turns are there? So this is 1, 2, 3 and 4. So there are 4 turning points. And notice the two ends here. The left side is downward, the right side is upward. We can say that the degree is odd, and we can also say that the leading coefficient here is positive. So these are the conclusions that we can draw. Notice that both end behaviors are generally dictated by the same way as that of the polynomial power functions. So if the right side is upward and the left side is downward, it's positive. If the left side was upward and the right side was downward, the leading coefficient would have been negative. So these are the conclusions that we can draw from this curve. Now, because there are 4 turning points, and if you consider that 4 is the maximum number of turning points, we can say that if this is n minus 1, then L will be nearly 5. So this is something that can validate the assumption here. So use the same principle now. So pause the video right here and try to conclude what you see from the graph. Next, you have given the function f of x equal to minus 2x times x minus 2 times x plus 3. So they're asking us to determine the local behavior. So now we have, so how many are there now? So from the first thing that we need to do is find the number of x-intercepts. How do you find x-intercept? Put f of x equal to 0. So 0 becomes equal to minus 2x times x minus 2 times x plus 3. So as per the rule, so you get x equal to 0, x minus 2 equal to 0 and x plus 3 equal to 0. So x equals to 2 and x equal to minus 3. So there are 3 x-intercepts. So which means that if you take the graph here, so the first bend starts at 0 here on the x-axis, which means that it goes upward like this and then comes downward at point 2 here and then goes upward. So let me draw it clearly. So let's do the next thing without drawing the graph. First thing next is, notice multiply all the x's, which means that the power, so the degree of the polynomial is 3, so which is power 3, which is odd. Now the second thing that we need to know is the leading coefficient is negative 2, which is negative. So which means that if you draw the curve, the end behavior is on the right side we have upward, on the left side we have downward, and we know the points. We have negative 3 here, 0 and 2 here. So when you draw the curve, we can say that this is the curve. So from the behavior here, so we know that we have negative 3 is one of the points, 0 and you have 2. So from the 3 values, and we know that the leading coefficient is negative and it's an odd function. So which means on the right side it's upward, on the left side on the left side it's upward and the right side it is downward. So from this we can say that the graph goes somewhat like this. So this is the graph of this is a rough sketch of the graph of the function. So this is how we can determine the function and the behavior, the local behavior of the function. So remember that here there is a maximum of 2 turning points, which is basically justified by the graph saying that if the degree is 3, so that there should be a total number of a maximum of 2 turning points. So use the same thing now and pause the video right here and try to solve this problem. So next let's talk about graphs of polynomial functions. So after you complete this section, you should be able to recognize the characteristics of graphs of polynomial functions. Use factoring to find the zeros of polynomial functions, identify zeros and their multiplicities, determine the end behavior, understand the relationship between degree and turning points, and finally graph the polynomials and use the intermediate value theorem. So let's start with the recognizing the graphs of the polynomial functions. So polynomial functions of degree 2 or more have graphs that do not have sharp corners. So they will always have, they will generally have a bent corner. So polynomial functions also display graphs that generally do not have no breaks. So curves with no breaks are called continuous graphs. Curves that do have breaks are called non-continuous graphs, and they are not polynomial functions. So they are asking us which of the functions represents a polynomial function here. So notice that there is no sharp corners. First thing means that we can eliminate this one, and there should be continuous curves, which means we can eliminate this one. So these two are polynomial functions. Next, finding the x-intercepts of a polynomial function using the graph. How would you find the x-intercepts here? So if you don't want to directly find it from the graph, we can say directly find it from the graph based on the points where it touches the graph, it cuts the x-axis. Here it cuts the x-axis at -3, -2 and 2. So these three represent the x-intercepts. The other way is to put h of x equal to 0 and find each individual value of x here. So this is how we can find the zeros directly from a graph. So pause the video right here and use the principle. So remember that for y-intercept, here we are going to put z of x equal to 0. For x-intercept, for y-intercept we are going to put x equal to 0. For x-intercept we are going to put z of x equal to 0. So pause the video right here and try to put the values and try to find the x and y-intercepts. Next, how to use factoring to find the zeros of the polynomial functions. So let's start with first thing, set f of x equal to 0. Now if the polynomial function is not given in factored form, factor out any common monomial factors. Second, factor any factored binomials or trinomials. Finally, set each factor equal to 0 and solve to find the x-intercept. So let's say we have been given this function here. How do you find the x-intercept for this function here? So we have x cubed plus 2x squared minus 9x minus 18. Now the first thing that we want to do here is to see if we can find anything common between the values here. Now between the first two values, x square is common. If you take x square common, you get x plus 2. And in the second one, 9 is common in both ones. So take -9 out, you get x plus 2. Notice that when you multiply the values, you get back the same equation. Notice that x plus 2 is common here. So if you take x plus 2 out, you get x plus 2 times x square minus 9. Which if you further simplify, x square minus 9 can be written as a square minus b square becomes a plus b into a minus b. So it becomes x plus 3 times x minus 3. So now you have everything. Put it equal to 0 now and find each individual value equal to 0. So it becomes x equal to -2, x equal to -3 and x equal to 3. So these here are examples of, this is the x-intercepts. So this is how you can factor by using the factoring principle. If there is any common terms that you can factor, so use that common terms and factor the equation. Now, so identifying the zeros and their multiplicities. So if a polynomial of a factor has a form x minus h whole to the power p, so which means that x equal to h is a zero of multiplicity of p. So the graph will pass through the axis and only touch the x-axis at 0 if the multiplicity with even multiplicities. So remember that, for example, let's say if you have a graph f of x equal to x plus x minus 2 whole square, that means the graph at the point 2 will bend in such a way and just graze the graph and go up, because the multiplicity here is even. If it is odd, then the graph will cross the axis. So with even multiplicities, they will just touch the x-axis. If odd multiplicities, they will cross the x-axis. with odd multiplicities. Now the sum of these multiplicities is the degree of the polynomial. So this is an example here. When you have single 0, so then it crosses the x-axis. When you have a multiplicity of 2, it grazes the x-axis. When you have a multiplicity of 3, it crosses the x-axis. So this is how we can determine the multiplicity. Now here, let's try an example here. So what is given here? They're asking us to use the graph of the function of degree 5 to identify the zeros of the function and their possible multiplicities. Now notice that negative 3 here, it crosses negative 3, and at 2 also, negative 2 also it crosses it, and at negative 1 it also grazes the graph, but it also crosses the graph. Now if the graph crosses the x-axis and appears almost linear, which means that there is a multiplicity of 0. But if you have a 0 with an odd multiplicity, it generally grazes the axis rather than directly crossing it linearly. Now notice that here at this point it's actually grazing the graph, which means that here this one we already have two zeros, which is negative 3 and negative 2, which means this here has to have an odd multiplicity. Now they are already given us that the degree is 5, which means that there is only 3 of them left, so this should be 3, which means that this point 1 here repeats itself 3 times. So this is how we can find the zeros of the function using their multiplicities. Now if it crosses it directly, then there is a single 0, which basically means that that value is only once. Now if it is odd, more than 0, so then it basically crosses the graph at the point 0. So use the same principle now. So pause the video right here and try to find the zeros of the multiplicity here. So notice that it grazes at negative 5, it is crossing the negative 5, and at negative 1 it is using the value, it touches negative 1, which means that here it should have an even multiplicity, here it should have an odd multiplicity. Again at negative 3 it's only touching it, which means that this should be even. So they have given us a degree of 9. So pause the video right here and try to justify the values of multiplicities that are there. So because notice that negative 1 here is grazing the graph directly and going over it, so we can consider that this should have something about 2. But here the graph is little more bent, so which means that this should have a value greater than 2. Now here also the value should be greater than 2. Now we have already divided 2, so there is only 7 left. So you have to divide 7 in such a way that you get one even number and one odd number. One way of getting that is 4, 3 or 2, 5. So which means that you can either have 3 negative 5s and 4 even ones, or 5 odd values or 2 even values. So this does not look like 2. So this does not look like 2. So we can basically think that this is not the value. So which means this should be about 3. I'm sorry. This should be about 4 and this should be about 3. So this is how we can justify the multiplicities. Now how do you determine the end behavior? It's similar again. If both are pointed upwards, it has a positive leading coefficient and it's a even degree. When you have a negative leading coefficient and even degree, both of them will face downwards. Now when you have an odd degree and a positive leading coefficient, on the right side it goes up, on the left side it goes down. When you have a negative leading coefficient, on the left side it goes up, on the right side it goes down. So this is how the end behavior generally works. Now understanding the relationship between the turning points, so the turning points themselves can show you where the points so these points are generally called as the points of inflection, where a function changes its behavior from decreasing to increasing or increasing to decreasing. So what are the maximum number of turning points in each polynomial? So the maximum number of turning points is n minus 1, where n is the degree of the polynomial. So n minus 1 is the maximum number of turning points. So pause the video right here and try to determine the maximum number of turning points for these two functions. So with that, we end lecture 2.